For medium and high voltage systems, the proper size for the equipment grounding conductor run with feeder conductors is based on National Electrical Code Section 250.122. This section requires the equipment grounding conductor to be sized based on the rating of the overcurrent device protecting the feeder conductors. For systems over 600 volts, the minimum size of the equipment grounding conductor is calculated using the formula in Table 250.122. Let's delve deeper into the specifics of National Electrical Code Section 250.122 and Table 250.122 to understand the proper sizing of equipment grounding conductors for systems operating at over 600 volts. The equipment grounding conductor plays a crucial role in electrical safety. It provides a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses. This rapid clearing of faults minimizes the risk of electrical shock and equipment damage. National Electrical Code Section 250.122 outlines the requirements for sizing equipment grounding conductors for various applications. However, the key point to remember is that for systems exceeding 600 volts, a specific approach using Table 250.122 is mandated. Now let's break down the process. The first step is to identify the rating or setting of the overcurrent protective device that is safeguarding the feeder conductors. This overcurrent device could be a circuit breaker, a fuse, or any other device designed to interrupt the flow of current when it exceeds a predetermined level. The rating of this device, expressed in amps, is the primary input for determining the appropriate size of the equipment grounding conductor. Once the overcurrent device rating is known, the next step involves consulting Table 250.122 in the National Electrical Code. This table provides a correlation between the overcurrent device rating and the minimum required size of the equipment grounding conductor. The table is structured in a way that allows you to easily find the appropriate conductor size based on the overcurrent device rating. It is imperative to use the correct table within the National Electrical Code. There may be different tables for different grounding scenarios. Make absolutely sure you are using Table 250.122. Now let's consider some examples to illustrate the application of Table 250.122. Firstly, assume that the overcurrent device protecting the feeder conductors is rated at 400 amps. You would locate the row in Table 250.122 that corresponds to an overcurrent device rating of 400 amps. The corresponding column in that row would then indicate the minimum required size of the equipment grounding conductor. This size would typically be expressed in terms of American wire gauge or kc mil. Secondly, if the overcurrent device protecting the feeder conductors is rated at 800 amps, you would locate the row in Table 250.122 that corresponds to an overcurrent device rating of 800 amps. The corresponding column in that row would then indicate the minimum required size of the equipment grounding conductor. Again, this size would typically be expressed in terms of American wire gauge or kc mil. Thirdly, imagine the overcurrent device is rated at 1200 amps. Find the 1200 amps row and read across the table to find the appropriate equipment grounding conductor size. Always remember to adhere to the specific instructions and notes provided within Table 250.122 and the associated sections of the National Electrical Code. These notes may contain important clarifications or exceptions that could affect the selection of the equipment grounding conductor size. It is also crucial to consider the material of the equipment grounding conductor. The table values typically assume the use of copper conductors. If using aluminum conductors, you may need to adjust the conductor size to achieve equivalent ampacity and conductivity. In addition to the minimum size requirements outlined in Table 250.122, there are other factors to consider when selecting equipment grounding conductors. These factors include the length of the conductor run, the ambient temperature, and the presence of any corrosive environments. Longer conductor runs may require larger conductor sizes to minimize voltage drop and ensure effective fault current clearing. High ambient temperatures can reduce the ampacity of conductors, necessitating the use of larger sizes. Corrosive environments may require the use of special conductor materials or protective coatings to prevent degradation and maintain the integrity of the grounding system. Furthermore, it is important to ensure that all connections within the equipment grounding conductor system are properly made and maintained. Loose or corroded connections can significantly increase impedance and reduce the effectiveness of the grounding system. All connections should be clean, tight, and protected from corrosion. Regular inspection and maintenance of the equipment grounding conductor system are essential to ensure its continued reliability. This includes visually inspecting conductors for damage or corrosion, testing connections for tightness and conductivity, and verifying the overall integrity of the grounding system. In summary, when sizing equipment grounding conductors for systems over 600 volts, always refer to National Electrical Code Section 250.122 and Table 250.122. The size of the equipment grounding conductor must be based on the rating of the overcurrent device protecting the feeder conductors. Consider all relevant factors such as conductor material, length of run, ambient temperature, and environmental conditions to ensure the selection of an appropriate conductor size. Proper installation, connection, and maintenance of the equipment grounding conductor system are critical for electrical safety and equipment protection. Now, let's discuss some additional considerations and potential challenges related to equipment grounding conductor sizing for medium and high voltage systems. Firstly, one common challenge is dealing with systems that have very high fault current levels. In such cases, the equipment grounding conductor size determined by Table 250.122 may not be sufficient to handle the available fault current. It may be necessary to perform detailed fault current studies to determine the appropriate conductor size to ensure adequate protection and prevent conductor damage during a fault event. Secondly, another consideration is the use of ground fault protection of equipment, or GFP. Ground fault protection is designed to detect and interrupt low-level ground faults that may not be detected by standard overcurrent protective devices. When GFP is used, the equipment grounding conductor must be sized to carry the maximum ground fault current that the GFP system is designed to handle. This may require a larger conductor size than the determined by Table 250.122. Thirdly, in some cases, it may be necessary to use multiple equipment grounding conductors in parallel to achieve the required ampacity and conductivity. When parallel conductors are used, they must be sized and installed in accordance with the requirements of the National Electrical Code. It is important to ensure that all parallel conductors are of the same material, size, and length, and that they are properly connected at both ends to ensure equal current sharing. Fourthly, it is also important to consider the impact of electromagnetic interference, or EMI, on the equipment grounding conductor system. EMI can cause unwanted noise and interference in sensitive electronic equipment. To minimize EMI, it may be necessary to use shielded equipment grounding conductors or to implement other EMI mitigation techniques. Fifthly, when working with existing electrical systems, it may be difficult to determine the original design criteria and the rationale behind the selection of the equipment grounding conductor size. In such cases, it may be necessary to perform a thorough investigation and analysis to ensure that the existing grounding system is adequate and meets current code requirements. Sixthly, it is also important to stay up to date with the latest revisions and interpretations of the National Electrical Code. The National Electrical Code is a dynamic document that is constantly evolving to reflect changes in technology and industry best practices. Failure to comply with the latest code requirements can result in safety hazards and code violations. Seventhly, it is advisable to consult with a qualified electrical engineer or a licensed electrician when designing or modifying equipment grounding conductor systems for medium and high voltage applications. These professionals have the knowledge and experience to ensure that the grounding system is properly designed, installed, and maintained in accordance with all applicable codes and standards. Eighthly, documentation is key. Maintain detailed records of all grounding system design calculations, conductor sizes, installation details, and maintenance activities. This documentation can be invaluable for troubleshooting problems, performing upgrades, and demonstrating compliance with code requirements. Ninthly, regularly inspect and test the equipment grounding conductor system to ensure its continued reliability and effectiveness. This includes visual inspections, continuity tests, and ground impedance measurements. Any deficiencies or problems should be promptly addressed to prevent potential safety hazards. Tenthly, consider using supplemental grounding electrodes in addition to the equipment grounding conductor. Supplemental grounding electrodes can help to improve the overall grounding system performance and reduce the risk of electrical shock. These electrodes should be installed in accordance with the requirements of the National Electrical Code. 11thly, when working with medium and high voltage equipment, always follow safe work practices and procedures. This includes de-energizing and locking out equipment before working on it, using appropriate personal protective equipment, and following all applicable safety regulations. 12thly, be aware of the potential for stray voltage on the equipment grounding conductor system. Stray voltage can be caused by a variety of factors, including unbalanced loads, inductive coupling, and capacitive coupling. Stray voltage can pose a safety hazard and can also interfere with the operation of sensitive electronic equipment. 13thly, consider using surge protection devices to protect equipment from voltage surges and transients. Surge protection devices can help to divert surge current away from sensitive equipment and prevent damage. 14thly, be mindful of the potential for corrosion of equipment grounding conductors, especially in harsh environments. Corrosion can significantly reduce the ampacity and conductivity of conductors, leading to grounding system failures. Use corrosion-resistant materials and coatings to protect conductors from corrosion. 15thly, regularly clean and maintain all grounding connections to ensure good electrical contact. Dirt, dust, and corrosion can increase the resistance of connections, reducing the effectiveness of the grounding system. 16thly, be aware of the potential for ground loops in the equipment grounding conductor system. Ground loops can cause unwanted noise and interference in sensitive electronic equipment. Use proper grounding techniques to minimize the risk of ground loops. 17thly, consider using fiber optic cables for communication and control signals to minimize the risk of electrical noise and interference. Fiber optic cables are immune to electrical noise and interference, making them an ideal choice for sensitive applications. 18thly, properly label all equipment grounding conductors and connections to facilitate identification and maintenance. Clear and accurate labeling can help to prevent errors and ensure that the grounding system is properly maintained. 19thly, train personnel on the proper procedures for inspecting, testing, and maintaining equipment grounding conductor systems. Properly trained personnel are essential for ensuring the continued reliability and effectiveness of the grounding system. 20thly, consider using a ground fault circuit interrupter, or GFCI, for personnel protection in areas where there is a high risk of electrical shock. GFCIs are designed to detect small ground faults and interrupt the circuit quickly, preventing serious injury or death. These considerations are essential for ensuring electrical safety and equipment protection in medium and high voltage systems.